Professor Alan Good will give the opening ceremony talk. He is Victor Weisskopf Professor of Physics at the Massachusetts Institute of Technology. He has been honored with a long list of awards, including the Dirac Prize and Medal, the Isaac Newton Medal and Prize, and more recently, the Kavli Prize in Astrophysics. As you all know, Professor Alan Good has pioneered the theory of cosmic inflection. The opening talk of this plenary session, part of ICHEP 2014, will be on inflationary cosmology and particle physics. Professor Alan.
How do I make the slide up here? Oh, good. Okay, today I'll be talking to you about the interface between particle physics and cosmology. Cosmology has actually become a major sub-branch of particle physics, and I actually only know about part of that, so I'll talk about the part that I know. I'll talk about the interface with inflationary cosmology in particular. On my first slide here, I have a picture of the Planck satellite, and I'll be talking to you a little bit about the data that Planck has given us about the universe. Next to that, I have a picture of the BICEP 2 telescope, whose role has played such an important piece of, at least of the news, and hopefully of the science as well. I should point out that many of you probably came here to hear Francois Englert, who was originally slated to speak in this slot. Unfortunately, I'm told he had an accident at home and fell and was unable to come to the conference. It's certainly too bad because Francois has played a crucially important role in particle physics. The Broud-Englert-Higgs mechanism is now an essential part of the standard model of cosmology, excuse me, standard model of particle physics, I'll get this right. And I think we would not know how to make any sense out of that model at all without the Broud-Englert-Higgs particle. There's a picture there of Higgs and Englert together. I'm told that that was actually the first time they met at the July 4th, 2012 announcement of the discovery of the Higgs particle. I, by the way, have never met Francois Englert either, but that's more plausible than the fact that Peter Higgs had never met him until 2012. And then one more picture of Francois at the press conference at CERN. So we certainly sorely miss Francois today and would have very much enjoyed hearing what he would have had to say. Coming back to my own talk, I want to begin by talking about just the conventional Big Bang theory in order to set up the distinction. Hold on a second while I get a better microphone here. More flexible one. Okay. Almost. Now I am. Is that right?
No, better.
Okay.
This is for your pocket.
Yeah, sure.
You don't have any mobile, right?
What?
Cellular, mobile phone?
I've got one. Should I turn it off?
Okay, perfect.
Good. Okay, here I am again. Now I can walk around, which makes me feel better. I want to begin by just saying a few words about the conventional Big Bang theory, that is the Big Bang theory without the addition of inflation. This theory certainly existed for many years before inflation and still plays a very important role in our understanding. The Big Bang theory is essentially the theory that the universe, as we know it, began at 13.8 plus or minus 0.5 billion years ago. I should emphasize that my use of the phrase "as we know it" was intentional. I do want to allow for the fact that we don't really know that existence began at the instant of the Big Bang. There certainly could have been a prehistory that we don't know much about, which would not be counted as part of the universe as we know it, but could very well have taken place. The Big Bang theory begins with an initial state of a hot, dense, uniform soup of particles, which, according to this version of the theory, filled space uniformly from the very beginning. The conventional Big Bang theory describes how the early universe expanded and cooled. It describes how the late chemical elements formed, and it describes how the matter congealed to form the stars and galaxies and clusters of galaxies that we observe today. And it is a very successful theory, even without inflation. And one of the nice things about inflation is that it maintains all of the successes of the original hot Big Bang theory while making up for some of its shortcomings. And shortcomings is what I want to talk about next. These are not things that the conventional Big Bang theory gets wrong. There are just a number of issues that the conventional Big Bang theory never addressed at all. In particular, the conventional Big Bang theory said nothing about what caused the expansion. It really is only the theory of the aftermath of a bang, even though we call it a Big Bang theory. It says nothing about what banged, why it banged, or what happened before it banged. Only talks about the aftermath. Secondly, the conventional Big Bang theory said nothing whatever about where all the matter came from in the first place. The theory assumed that all the matter existed from the very beginning, if not in its present form, in some perhaps precursor form. But it was all there from the very start in the context of the conventional Big Bang theory. Now to move on to inflation. Inflation is a modification of this conventional Big Bang theory, and it takes the form of a prequel. It talks about what set up the initial conditions for the conventional Big Bang theory description. And in particular, inflation can explain the bang of the Big Bang, by which I mean what drove the outward propulsion. And inflation describes that outward propulsion in the form of something which I consider to be kind of a miracle of physics. I'm going to be suggesting that inflation is based on two miracles of physics, of which this is the first. And by miracle of physics, I'm of course not referring to anything that I consider to be supernatural, but rather I'm referring to features of the laws of physics, which are A, very different from what I happen to have learned in high school, and very likely what you've learned in high school as well, and two, play such an important role in our current thinking that it really changes our viewpoint of the universe as a whole. So one of these, this first miracle of physics, is the fact that gravity is not always attractive. Gravity can be repulsive, and in fact, inflation attributes the propulsion of the Big Bang to a repulsive form of gravity. Now, this repulsive form of gravity was never possible in Newtonian physics, which is why we didn't learn about it in high school. In Newtonian physics, gravity is always attractive, but in the context of general relativity, gravity can be attractive or repulsive. And in particular, it comes about because pressures, as well as energy densities, can serve as a source of gravitational fields in the context of general relativity. And a negative pressure can create a repulsive gravitational field. And that's exactly how inflation works. Negative pressure implies repulsive gravity, and what particle physics tells us is that a state whose energy is dominated by the potential energy of a scalar field, in fact, necessarily has a negative pressure and will therefore create a repulsive gravitational field. And that really is the underlying physical basis behind the workings of inflation. There are basically two scenarios, two types of scenarios that are described in terms of present-day ideas about inflation. One of them is called small field. Originally, it was called new inflation, which is a situation where the scalar field is sitting on the top of a local maximum of the potential energy function and then gradually rolls off. And while the scalar field is sitting on top of that hill, where the universe would be in a state which we call a false vacuum, and that would be one example of a state whose energy is dominated by the potential energy of the scalar field. The alternative possibility, large field or chaotic inflation, was originally proposed by Linde in 1983. And in that version of inflation, you can have a potential that's shaped almost any old way. It's a much more flexible idea. And the point is that if the scalar field starts high enough on the hill, then as it rolls down, inflation will take place. And one can build very successful inflationary scenarios of that sort as well. So the basic scenario is that we begin with the assumption that the early state of the universe, whatever it was, and we don't have a very good theory of how the universe ultimately originated, but we assume that whatever the early state of the universe was, it contained at least a small patch of this negative pressure material that would drive gravitational repulsion. And if inflation took place at the scale of grand unified theories, which is at least one plausible possibility, and is what I'll use for my numerical examples, that patch need only be as large as 10 to the minus 28 centimeters, which is, as you realize, an incredibly small size, more than 1 billion times smaller than the size of a single proton. Now, since the patch is going to be enlarged fantastically by inflation, the initial density of such patches could have been extraordinarily low, and it wouldn't matter. By the end of inflation, those tiny patches would still dominate the universe that would then exist. The gravitational repulsion created by this negative pressure then becomes the driving force of expansion of that tiny region, which becomes the Big Bang of at least that region. The patch is driven into exponential expansion by this gravitational repulsion, with a time constant, if we're dealing with grand unified theory scales, of about 10 to the minus 38 seconds. The patch needs to expand by a factor of at least about 10 to the 28, which requires only 65 e-foldings of expansion. It could have expanded much more than that. We don't really care. But this minimal amount of inflation is required to produce a universe as big as what we observe. At the end of this time, the region that's going to evolve to become our observed universe is only about 1 centimeter across, although the universe as a whole could be much larger than that. We have no way of knowing. From then on, the universe coasts until it becomes as large as what we see today. Inflation is ended because the scalar field eventually rolls down the hill of this potential energy diagram and then oscillates about the minimum of that potential energy diagram. And in doing so, it releases all of its energy, which then produces a hot soup of ordinary particles, which rapidly reaches thermal equilibrium and becomes the starting point of this conventional Big Bang description that I talked about one slide ago. So by this scenario, inflation can set up the initial conditions which had always been assumed in the context of the conventional Big Bang theory. But now we don't have to assume them. Now we can understand where they come from. An important feature is that as this region underwent this fantastic expansion by at least a factor of 10 to the 28 in each direction, the energy density that was stored in that scalar field was not lowered, which means that the scalar field is behaving very, very differently from ordinary matter that we're accustomed to, like the gas that fills this room. As the expansion took place, the energy did not go down. So even though more and more mass or energy was appearing in this region filled with the scalar field, somehow total energy was conserved, even though the energy in the scalar field has gone fantastically upward. So how can that happen? That requires another miracle of physics. So this is my second miracle, which I think is necessary to understand the basics of how inflation works. The point is, although energy is definitely conserved, it's not always positive. And in fact, the energy of a gravitational field is strictly negative. And this fact is true in Newtonian physics as well as in general relativity. So what's happening during inflation is that the positive energy that's appearing in the form of the scalar field, which is now occupying a larger and larger region, is compensated by the negative energy of the gravitational field, which is also filling a larger and larger region as the inflation takes place. So the total energy remains exactly constant during this inflationary process and could be exactly zero. There could very well be a perfect cancellation between the energy of ordinary matter, initially in the form of a scalar field, and the energy of gravity itself. So the balance sheet then can be shown very simply. The total energy of the universe, or at least the piece of the universe that we're now looking at, would consist of a black contribution and the positive contribution of matter and radiation, but it would be precisely canceled by a negative contribution, shown in red, for gravity, adding up to a big zero for the total energy of the universe. And it's really crucial for inflation to be able to create a universe out of essentially nothing, that it really does not take any energy to produce a universe. And that in itself is, I think, a very startling fact, but a very clear consequence of the laws of physics as we know them. So that finishes my description of the scenario of inflation. What I'd now like to do is move on to talk about the evidence that we have that our universe really did undergo this process that we call inflation. So I want to talk about 4 pieces of evidence altogether. The first will be the large-scale uniformity of the universe. The fact that the universe looks the same in all places if we average over large enough scales. This large-scale uniformity shows up most clearly in the cosmic background radiation, which has now been measured to rather extraordinary precision. And what astronomers have found is that this radiation has the same temperature and the same intensity in all directions to an accuracy of about 1 part in 100,000, which is really pretty incredibly uniform if you think about it. And the question is, how did that happen? How did it come to be so uniform? Now, if you're willing to just assume that the universe started out completely uniform, then there's no question. You're free to assume that if you want, and then this question goes away. But if you would like to have some kind of a dynamical explanation for how the universe became so uniform, then an important question arises, which is what we're discussing here. If we think about the history of the cosmic background radiation, it was released when the universe was about 380,000 years old. And by that, what I mean is that prior to that time, the universe was so hot that the gas that filled the universe was in a plasma state. The electrons had been ripped off the atoms. And that kind of a plasma is very opaque to radiation. The photons that make up today the cosmic background radiation would have existed at those early times and would have been traveling at the speed of light at those early times. But instead of continuing in a straight line, the photons would constantly be scattering off of the free electrons of the plasma, changing their direction each time they scatter. And the net effect is that the mean free path of a photon in that situation would be so short that the photons would not have gone anywhere, effectively, during these first 380,000 years. They would just oscillate in a tiny oscillation pattern. Then, however, at 380,000 years, according to our calculations, the universe cooled enough so that the plasma neutralized and became a neutral gas, like the air that fills this room, which is vastly more transparent to photons. So the photons that we observe today in the cosmic background radiation have been essentially moving on straight lines since 380,000 years after the Big Bang. And what that means is that the cosmic background radiation is really showing us an image of what the universe looked like at 380,000 years, just like the photons traveling from my eyes to your face, from my face to your eyes. Oh boy, I need more sleep. Just like the photons traveling from my face to your eyes allow you to figure out what my face looks like. So the bottom line here is that the universe was incredibly uniform by 380,000 years after the Big Bang. Now, can we explain that? Well, without inflation, you really can't. And the reason why you can't is pretty simple. We can trace back those photons that we're observing, say from 2 opposite directions in the sky, and figure out where they came from at 380,000 years after the Big Bang. And in the context of cosmology without inflation, those 2 origins of those 2 photons were separated from each other when the photons were emitted by a distance that was about 100 times the distance that light could have traveled up until that time. So since nothing, as far as we know, travels faster than light, it means that there's no way that the photon originating over there could have had any information whatever about the photon originating from the other side. Yet somehow they knew how to be at the same temperature at the same time to an accuracy of 1 part in 100,000. So how in the world could that have happened? Within conventional cosmology, there really is no answer, except maybe to assume that everything started out completely uniform for reasons unknown. But in inflationary cosmology, there's a very simple explanation, because the facts that I just told you change. In inflationary cosmology, one is inserting into the history of the universe a period of rapid exponential expansion. And that means that if we look at the region that we're observing today and follow it backwards in time, when we go through the era of inflation, it contracts tremendously. So before inflation, the universe was vastly smaller than we ever would have thought otherwise. And that's this number I gave you, of perhaps 10 to the minus 28 centimeters across. During this pre-inflationary stage, when the universe was incredibly tiny, there was plenty of time for that tiny region to become uniform by exactly the same kind of processes by which the air in the room reaches a more or less uniform temperature if you let it sit. Then, once the uniformity is established on this tiny, tiny scale, inflation can take over and stretch this tiny region so that today it's large enough to encompass literally everything that we see. So we have a very simple explanation now of why everything that we see looks uniform. It's because it all came from an incredibly tiny uniform region in the very early universe. So that's what I have on the slide here. So that's the first very important success for inflation in terms of explaining features that we already knew that the universe has. Second thing I want to talk about is what's called the flatness problem, which is the question of why was the early universe so flat? And by flat, I mean obeying Euclidean geometry, which in the context of general relativity is by no means a foregone conclusion. If we assume that the universe is homogeneous, the same in all places, and isotropic, the same in all directions, then geometry really only allows 3 possible geometrical structures. We could have a closed geometry, like the surface of a sphere, an open geometry, like a saddle shape, or just on the borderline between those 2 possibilities is the possibility of a flat universe, one that obeys all of the axioms of Euclidean geometry. These pictures are supposed to illustrate that in a closed geometry, a triangle has more than 180 degrees for the sum of the 3 angles. Open geometry, less than 180 degrees, and only for a flat geometry do we get what Euclid told us, that the sum of the 3 angles should always equal exactly 180 degrees. In general relativity, this issue of the geometry of space is linked to the mass density of the space, and cosmologists define this quantity called omega, which is just the ratio of the actual mass density, whatever it is, to the critical mass density, where the critical mass density depends on the expansion rate and defines that mass density which would make the universe exactly flat. So that means that if omega is exactly equal to 1, the universe is flat. If omega is greater than 1, the universe is closed. If omega is less than 1, the universe is open. Now, what makes flatness particularly hard to understand is the fact that under the conventional evolution of the universe, omega equals 1 is an unstable equilibrium point. And that means it's like a pencil balancing on its tip. If omega in the early universe were exactly equal to 1, it would be like the pencil being exactly straight up. And if we pretend that we could treat the pencil classically rather than quantum mechanically, if it was exactly straight up, it would stay exactly straight up forever. It wouldn't know which way to fall. But if the pencil were leaning just a little bit in any direction, it would rapidly start to fall in that direction. And that phenomena of instability is exactly the way omega behaves with regard to omega equals 1. If omega in the early universe were just slightly greater than 1, it would rapidly rise to infinity, and the universe would recollapse. And going in the opposite order here, if omega in the early universe was just slightly below 1, it would rapidly fall to 0. And then there would never be a possibility of forming any galaxies or any structure. So for the universe to look anything like what it looks like, omega had to have been extraordinarily close to 1 in the early universe. And to say something quantitative, to be as close to the critical density as we measure today, if we go back to 1 second after the Big Bang, which, by the way, was the beginning of the nucleosynthesis processes, which are in fact related to a very successful prediction of Big Bang physics, at 1 second after the Big Bang, omega must have been equal to 1 to an incredible accuracy of 15 decimal places. Yet, in the context of conventional Big Bang cosmology, there was never anything which fixed the initial mass density of the universe. It could have been anything. So there's no explanation in the context of conventional cosmology of how omega got to be so incredibly fine-tuned to be incredibly near the value of 1. So that's the mystery. In inflation, there's a simple solution. In inflation, the expansion rate is not arbitrary. The expansion is driven by this repulsive gravitational force. And that, because it is repulsive, changes the equations that describe how omega behaves. And during the inflation era, instead of omega being driven away from 1, as it is during all the other eras in the universe, inflation drives the universe to just the right expansion rate to make omega 1. So omega is driven towards 1 during inflation, and in fact extremely rapidly, exponentially fast. And that means that before inflation, omega could have been essentially anything. Before inflation, omega could have been 2 or a half or 10 or 1,000 or 1/1000th. The further away you start from 1, you'll need a little bit of extra inflation to drive omega to 1 closely enough. But that's certainly not a problem. We expect there's very likely much more inflation than the minimal that's necessary. Inflation explains to us why it was that omega in the early universe was so extraordinarily close to 1, as we know it must have been. This actually leads to a prediction, because this mechanism by which inflation drives omega to 1 is so effective that unless you arrange for inflation to end at just the right place exactly, the mechanism will essentially always overshoot and give us a universe that's not just as flat as what we see, but a universe that's effectively completely flat as far as we can tell. So there's a prediction that even today the universe should have a critical mass density. However, until 1998, astronomers mostly believed that omega was somewhat less than 1, and they were converging on a number of about 0.2 or 0.3 as we went into 1998. So inflation was looking like it was not giving us the right prediction. Now, I should add on a personal note that this was a source of particular discomfort to me, especially when I had dinner with astronomers. They would always look at me and sneer a little bit and say, yeah, inflation is a very pretty theory. We understand that, but it can't be right because inflation predicts omega is 1, and it's pretty clear that omega is not 1. Omega is only something like 0.2 or 0.3. But fortunately, that situation changed dramatically in 1998, and now I can say that the most accurate prediction we have for the mass density of the observed universe comes from this Planck satellite, combining it with some other observations, and omega is now equal to 1 to an accuracy of about 0.5%. The big change that happened in 1998 was the discovery that the universe is not slowing down under the influence of gravity, but instead today the universe is actually accelerating. This acceleration, we believe, is being driven, present tense now. This acceleration, we believe, is being driven by a repulsive form of gravity, just like inflation in the early universe. And the stuff that causes it, the stuff that has the negative pressure, that's the only way we know how to do this, is what we call the dark energy. And we don't know exactly what the dark energy is, but we can nonetheless figure out how much of it there must be to drive the acceleration that we observe. And when that gets added to what we already knew existed of 0.2 or 0.3, we end up with this new number for omega, which is now almost exactly equal to 1 and known to be equal to 1 to an accuracy of about 0.5%. So what had been a significant failure of inflation is now a spectacular success of inflation. Okay, third, and this is another spectacular success of inflation, besides the fact that the universe on very large scales looks very homogeneous, on smaller scales, we know that the universe has all kinds of structure. There are galaxies, clusters of galaxies, planets, stars, et cetera. This structure in the universe today is reflected in the cosmic background radiation, which shows the conditions at 380,000 years. I told you that it was uniform to 1 part in 100,000, which is true. But at the level of 1 part in 100,000, there really were ripples in the mass density of the early universe, ripples which now show up as ripples in the cosmic background radiation, which, thanks to marvels of fantastic technology, can now be measured to extraordinary accuracy. And an important question, of course, becomes, where did these ripples come from? Now, in conventional Big Bang cosmology, there was never an explanation for the homogeneity in the first place, so you might guess very well that there was also no explanation for why the homogeneity was not perfect. At that time, people knew there must be ripples to account for the subsequent evolution of structure, but those ripples were just put in by hand. They must have been there, people knew, but nobody had any idea where they came from or what determined the patterns of those ripples. In inflation, there's a remarkable new possibility. In inflation, we attribute these ripples to quantum fluctuations. Classically, the tremendous expansion of inflation would just smooth everything out by stretching. If you stretch anything enough, it becomes very smooth. And for a while, we were worried that inflation was going to predict a completely smooth universe, which would then never form galaxies. But early on, it was realized that quantum theory can come to our rescue, where the classical theory is predicting a completely smooth background. The quantum theory, due to the intrinsic uncertainty of quantum mechanics, will necessarily predict that in some places, the mass density will be slightly higher than the classically predicted average, and in other places, the mass density will be slightly lower than the classically predicted average. And that would give rise to a set of ripples, faint ripples on top of an almost uniform background. And that's exactly what we see. And in the context of inflation, we can even calculate what these ripples should look like. Now, I should qualify things a little bit here. If we really understood the physics of inflation, the physics of that scalar field that I showed you sample diagrams about, if we really knew that physics, we could calculate everything about these ripples. We, in fact, don't know much about those curves. We don't really know what scalar field drove inflation. It's, by the way, called the inflaton for obvious reasons, but we don't really know what this inflaton is or what exactly its potential energy function was. And therefore, we're not able to predict the intensity of these ripples. So we have to take the intensity of the ripples from the data. But nonetheless, even though it's in principle model dependent, all simple models of inflation, and by simple I mean a scalar field rolling down a hill that has no particularly sharp features, all simple models of inflation make essentially the same prediction for the spectrum of these fluctuations. And by spectrum, I simply mean how the intensity of the fluctuations varies with the wavelength. Exactly what we mean if we were talking about the spectrum of a sound wave. In fact, one could think of these waves as being very much like the way we think about sound waves. So inflation makes a prediction for the spectrum, and the remarkable thing is that so far, the data measured agrees really beautifully with the predictions of inflation. And the best data we have comes from the Planck satellite. So this is the Planck data that was released in March of 2013. And the little red dots with the error bars are the data. The greenish line is the prediction of inflation. To be honest, it's a 6-parameter fit, but of those 6 parameters, 4 of them are parameters that we know pretty well from other arguments. There are only 2 that are really being fit to the data. As you see, it's an absolutely stunning agreement. There are a few minor anomalies. People worry about them being a little bit low in this region, and there are a few other oddities that people point to, but none of these oddities are more significant than 2 to at most 3 sigma. By and large, it's a total success for inflation, which is just mind-boggling, I think, considering that this really comes out of pure thought. That is, we don't, it's hard to imagine how you know anything about the fluctuations of the cosmic background radiation, which we are actually claiming here were produced at 10 to the minus 38 seconds or something. So I think it's absolutely flabbergasting that it works so spectacularly well. Finally, I want to talk about gravity waves, which are also a prediction of inflationary cosmology. And gravitational waves have possibly been found by the BICEP2 experiment. I say possibly because there is some controversy now about these observations. So from the beginning, I think everybody realized that they would have to be corroborated before we could really rely on them, and that's the situation now. But if they are corroborated, and I think there's still a reasonable hope that that will happen, I do hope that will happen, they will provide a very strong piece of evidence for inflation in addition to the ones that I already mentioned. The physics point is that along with these density perturbations, inflation also predicts gravitational waves. And the mechanism is very similar. Quantum effects on very short length scales imply that everything fluctuates on very short length scales. And of those everythings that fluctuate, it includes fluctuations of the gravitational field itself, which really means fluctuations of the metric of space-time. And we expect from quantum theory that these fluctuations certainly should be there on very short length scales. And the role of inflation is simply to stretch these microscopic fluctuations to become large enough so that they can be observed, and in fact even become astronomical in size. And when they are stretched to astronomical sizes, they then start to behave essentially as classical gravitational waves, just as those waves were described by classical general relativity. These gravitational waves can be seen by BICEP because they perturb the plasma of the early universe, and in doing so, they imprint a pattern on the polarization of the cosmic microwave background. And this imprinting happens at 380,000 years after the Big Bang, where information is transferred from the gravitational waves to the patterns of the polarization of the cosmic microwave background, and that is what is currently being observed. Now, if these observations hold up, they really are incredibly important, not just to inflation, but to a lot of things having to do with our understanding of physics itself. First of all, it would be the first direct experimental evidence that gravity is quantized at all. Now, as far as I know, essentially all theorists believe that gravity has to be quantized because we don't really know any simple way that you could imagine coupling a classical theory of gravity to a quantum theory of matter. So for that reason alone, we're pretty sure that gravity has to be quantized. But nonetheless, if these observations hold up, this will be the first direct experimental test that we've ever had that gravity is quantized. Furthermore, it will be the first image that we have ever seen of a gravitational wave. Previously, we have verified energy loss in binary pulsar systems that we associate with gravitational radiation, and it works out just right. But that tells us nothing about what the wave actually looks like. While here we are really seeing the wave itself in the way it imprints itself on the polarization of the cosmic background radiation. And finally, besides just confirming that an effect predicted by inflation exists, if this gravitational radiation coming from inflation is real, it tells us something important about inflation, which we otherwise really have no way of knowing. An important ignorance that we have about inflation is the energy scale at which it took place. There's a wide range of possibilities for that, all of which are completely consistent with everything we know about inflation so far, with the exception of these gravitational waves. The higher the energy scale of inflation, the more intense these gravitational waves are, because the faster the expansion was at the time of inflation. And it's really just expanding ordinary fluctuations in the metric, which are always there, which is what we're seeing. So the faster the expansion, the more intense is the radiation that we observe. So BICEP2 found that this quantity called R, which is the ratio of the power in gravitational wave perturbations to the power in density perturbations, has a value of 0.20 with error bars. If that's right, then it tells us what the energy scale was, the energy density of the universe at the time of inflation, which I'm calling here rho sub INF. Rho sub INF is equal to 2.2 times 10 to the 16th GeV to the 4th power, in units where h bar and c are equal to 1, times the ratio r over 0.2. So if r is 0.2, the energy scale of inflation is 2.2 times 10 to the 16th GeV. And you might recognize that that's really exactly the energy scale of grand unified theories. So if this observation is right, there's at least an important circumstantial piece of evidence here that inflation is related to grand unified theories. Now, the history of BICEP2 has been something of a roller coaster ride for those of us who have been following it. It starts on March 17th, 2014 with the press conference. At the press conference, the BICEP2 team announced the detection of primordial B modes and the polarization of the cosmic microwave background. At the same time, they posted a paper. Whoops. Where did I go here? Okay, there. At the same time, they posted a paper which stated that the observed B-mode power spectrum is well fit by a lensed lambda CDM plus tensor theoretical model with a tensor to scalar ratio of r equals 0.20, just like I said. And they said with r equals 0 disfavored at 7 sigma. So that even tops the discovery of the Higgs particle, which was, I think, 5 sigma. Subtracting the best available estimate for foreground dust modifies the likelihood slightly, so that taking into account the confusion of dust, the confidence of r equals 0 is now disfavored only at 5.9 sigma. Still a whopping, unbelievable finding. So at the time, it seemed to all of us that we had here a fantastic piece of evidence that gravitational radiation coming from inflation really had been found. And that still may be true. I hope it's true. But since then, important doubts have been raised. The rumors started to circulate at the beginning of May, and those rumors led to a more concrete talk on May 15th by Raphael Flauger, one of the people involved in this study, who gave at that time a talk at Princeton, which was posted on the web in video form. And he concluded that, according to all estimates, foregrounds may be small enough to detect a large primordial signal at 150 gigahertz. That's the frequency of BICEP2, without foreground subtraction. In other words, it's possible that BICEP2 was right, but the uncertainty on foregrounds is large, and measurements at other frequencies, especially above 150 gigahertz, for example, from Planck, seem important for a definitive measurement. So Flauger was saying that the measurements of BICEP2 might be right, but they're certainly not definitive. The next day, there was a conference at Caltech where Matthias Zaldarriaga spoke, reaching very similar conclusions. I believe the case in favor of a detection of primordial B modes is not convincing, hopefully just temporarily, he added. A paper got published on May 22nd by Morton and Seljak, reaching similar conclusions. Another paper on May 28th by Flauger, Hill, and Spergel, reaching similar conclusions. And then on June 19th, the BICEP2 people posted a revised version of their paper, which was the version that was accepted for publication in Physical Review Letters. And they revised their conclusions a little bit too, although they're still basically sticking to their belief that what they've seen is a real indication of primordial B modes. They wrote that we examine a number of available models of polarized dust, that's the key issue of possible contamination, and find that at their default parameter values, they predict power 5 to 10 times smaller than the observed excess signal. And then they had with no significant cross-correlation with our maps. Then they have a sentence here which is a bit of a confession, although there's an if. They wrote, however, these models are not sufficiently constrained by public external data to exclude the possibility of dust emission bright enough to explain the entire excess signal. So they seem to be saying that the entire excess signal could conceivably be explained by dust, but it is qualified by this constrained by external public data, which means they're not telling us anything about what they would conclude if they used everything they knew. So exactly what they mean by that, we still really have to wait to find out. Current rumors are that the Planck team is working on a paper describing their dust measurements in the BICEP2 field, and this paper could be released any time now. I was told 5 weeks ago that it would probably be released in 3 weeks, so any time now. They also intend to release a full paper on polarization in October or November coming up. And it was just announced a few days ago that the BICEP2 and Planck teams are negotiating to collaborate on a paper that would pool their data, providing the clearest analysis of the situation. And that will possibly be finished by the end of this calendar year. At this very conference, by the way, tomorrow at 18:30, there will be 2 talks, one by Roger O'Brien for the BICEP2 team and one by Enrique Martinez-Gonzalez for Planck. They may resolve the whole situation tomorrow. We'll have to wait and see. I'm anxious to hear those talks. Before I finish, there's one other issue I'd like to, oh, I'm sorry. Before I get to that, something else I was going to say here. Suppose the BICEP2 observations turn out not to be primordial B modes. I think it's very important to emphasize that that is not, by any means, a real problem for inflation, although given all the fuss that's been made, it does become something of a problem in the public relations. But inflation is certainly still okay, even if these observations are not confirmed. Many plausible, simple inflationary models predict gravitational waves that are smaller than 0.20, and in fact, often smaller by many orders of magnitude. And furthermore, this was by no means the only success of inflation. As I've already told you, inflation also explains the uniformity of the universe, for which we don't really have any other completely well-formulated explanations. Inflation explains the flatness of the universe and predicts the mass density within 0.5%. Inflation predicts the spectrum of the density perturbations seen in the cosmic microwave background to extraordinary precision. And inflation also predicts, something I've not spoken about, that the perturbations in the CMB should have a Gaussian probability distribution, which has now also been tested to rather extraordinary accuracy. And to better than 1 part in 1,000, actually, we know that the probability distribution exemplified by the fluctuations in the cosmic background radiation have the Gaussian form that would be predicted by the quantum fluctuations coming from inflation. If BICEP2 turns out not to have seen primordial gravity waves, then we really don't know what intensity they might have. BICEP2 could only have seen them if they were really at the upper end of a very large region of uncertainty about what the intensity of those fluctuations are. So if BICEP2 has not seen them, it doesn't mean that they're just around the corner as soon as somebody has a slightly better experiment. They could be vastly far away. It's possible that the actual level of the gravitational radiation is so low that it will never be seen anytime in the foreseeable future. We just don't know. Okay, before I finish, there is one other topic I want to talk about 2 slides of, because I think it's an important topic, and it will come up in questions if I don't talk about it initially. And that is, inflation is often linked to discussions of the multiverse, and I think for good reason. If you hate the idea of a multiverse, you can still love inflation. I welcome you to do that. Inflation can happen without a multiverse. But it turns out that most detailed models of inflation, in fact, lead to what we call eternal inflation, meaning inflation that once it starts, it never stops. And that leads to a multiverse. So I think if we take inflation as a successful theory, and it certainly seems to be, we should also take seriously at least the possibility that our observed universe is not unique, but in fact is simply the result of one of many, many big bangs that occurred at different times in different places, and perhaps an infinite number of them. The way we led to that is that, roughly speaking, inflation is driven by a metastable state, which decays with some kind of a half-life. And it's easiest to think about this new form of inflation, or small field inflation, where inflation starts by the field sitting on the top of a hill. That's a perfectly clear metastable state of exactly the kind I'm talking about. And the point is that after one half-life, half of the inflating material will become normal, non-inflating matter, but the half that remains will continue to exponentially expand. And the exponential expansion is always vastly faster than the exponential decay, so it wins. The material that's left inflating at the end of this half-life is in fact vastly larger in volume than what you started with, even though half of it has decayed. The remaining half has just grown by so much. And there's nothing to stop that from going on again and again and again. So within the context of these models, once started, inflation goes on forever, with pieces of the inflating region undergoing decays, which will then cause them to break off and produce what we call, in this context, pocket universes. And we would be living in one of these pocket universes, and over time, an infinite number of these pocket universes would be generated, which is what we call a multiverse. Now, one success of this multiverse idea, which I think is one of the things that makes it attractive to think about, we might just assume the multiverse is meaningless. We don't care about it. Whatever's out there is out there. We would just like to explain our own universe. But our own universe has a very peculiar feature which we don't know how to explain, and that is the smallness of the energy density of the vacuum, which is the same as the cosmological constant. The vacuum energy density in our universe has now been effectively measured by the acceleration to have some non-zero value, but that non-zero value is vastly smaller than what we might have expected by about 120 orders of magnitude. That is, it's 120 orders of magnitude smaller than the Planck scale, which is really the only scale we know of in this theory that would set a natural value for the vacuum energy density. And particle theorists have spent many, many years thinking hard about this question, and so far nobody has really come up with a good dynamical explanation for why the vacuum energy should be so vastly smaller than the order of magnitude that we would naturally expect. So the multiverse offers a possible, although I have to say controversial, solution to this problem, and you've probably heard it before. It's called the anthropic solution. If there are many different types of vacuum, and string theory happens to predict that there are probably more than 10 to the 500 different types of vacuum. So let's assume that something like that is true, whether or not string theory is true. Then each of these would have their own vacuum energy density. And then there will be many types of vacuum that will have vacuum energies as small as what we observe, even though there would be a tiny, tiny fraction of all types of vacuum. Now, the vacuum energy is not just some number that sits alongside as everything else goes on. The vacuum energy has a strong effect on the evolution of the universe. In particular, the vacuum energy affects the cosmic evolution through the acceleration. If it's large and positive, the universe would just fly apart, and nothing interesting would happen. If the vacuum energy were large and negative, the universe would rapidly implode and disappear, and nothing would happen. So it is very plausible that life can only form in those pocket universes with incredibly small vacuum energies. And if that is the case, then even though in most of the multiverse the vacuum energy would be huge, typical in magnitude of the Planck scale, all or almost all living beings would observe a very, very small vacuum energy. And that could be the reason why we, as living objects, observe an incredibly small vacuum energy. So that's at least one possible explanation. It's not one that makes most particle physicists the happiest, but I guess Steve Weinberg pointed out that there's nothing in the laws of physics which implies that the laws of physics have to make theoretical physicists happy. So maybe this is the right explanation. There are people who claim it's unscientific. I think that's nonsense. It could be the right explanation. And if it's the right explanation, we'd better call it science, because we'd like to think that science is simply the search for the right explanations. And I think this is a possible explanation, and it's even, right now, I think the best explanation that we have. So to close, I just want to introduce a few quotations to give you an idea of the extent to which theorists take these ideas seriously. At a conference a few years ago, Martin Rees was asked, what he thought about the multiverse and how certain he was about it. and he said that he was sufficiently confident about the multiverse to bet his dog's life on it, which is pretty significant. I don't know Martin Rees's dog, but I assume he's cute and cuddly. Andre Linde at the same conference chimed in to say that he was so confident in the multiverse that he would bet his own life. Steve Weinberg was not at this conference, but he commented on it later. And he wrote that I have just enough confidence about the multiverse to bet. See if you can guess what comes next. Weinberg said he has just enough confidence to bet the lives of both Andre Linde and Martin Rees's dog. Now, I'll stop there. Thank you.
So we have time for questions, comments. What's there? Bill Bardeen. And next is...
Does evidence for quantum fluctuations in the early universe allow an independent measurement of h-bar?
Good question. The question was, I guess you could hear it, it was amplified. The answer, I think, is that at present it would not, because at present it would be determining the expansion rate of the universe at the time of these gravitational fluctuations. If we had independent evidence of that, because, for example, someday we might really know all of the underlying particle physics, then h-bar comes into that calculation, and it would allow a measurement of h-bar. We'd be able to directly measure the gravitational fluctuations. But right now we cannot because it's confounded with our lack of knowledge of the expansion rate of the universe at the time.
Sorry if these questions are too naive, but could you just explain when the universe expands faster than the speed of light, does that mean there's information transfer faster than the speed of light? And also, are there any observable consequences of a potential multiverse that's known at this time?
Okay, two questions there, totally independent. First, faster than light travel. It is certainly true in the context of inflationary cosmology that the size of what will become the observed universe increases at a rate which is vastly larger than the speed of light. I should also point out that even in the conventional Big Bang theory, before inflation was predicted, it was also true that the size of the region that is destined to become the visible universe today increased at a rate which was vastly larger than the speed of light. This does not violate general relativity and does not really mean that information is being transferred faster than light. The important thing here is that general relativity is the operant theory. And in general relativity, it's still true that nothing travels faster than light, but you have to be a little bit more careful about what exactly that means. What can be said definitively in special or general relativity is that if a particle has a race with a light beam, starting from the same place, the light beam will always win. So in that sense, nothing can ever overtake a light beam. Nothing goes faster than light. What makes general relativity a little bit more complicated for this issue is that in general relativity, space is not rigid. Space can bend and twist and stretch, and in particular, stretching is what's important here. General relativity places no limit whatever to how fast space can stretch. So if I have a particle over here and a particle over here and space in between, that space in between can stretch, and the distance between these particles can grow at a rate which is arbitrarily large compared to the speed of light, and it does not constitute transmission. If you wanted to send a signal from one to the other, it wouldn't get there because the space would be stretching too fast. A signal propagating through space can only move at up to the speed of light, but space can stretch at any speed it wants to in general relativity. Second question, remind me? Oh, experimental consequences of the multiverse. Right. In principle, there's a possibility, which is nice to know, at least to believe that we're not talking total fairy tales. We're talking about something which could conceivably be seen. And that is that these different pocket universes that form are really all forming in the same original inflating space-time. And that means that if they start out close enough together, they could collide. So there could be a collision of pocket universes in our past. And astronomers have even looked for such things. It would show up as a circular pattern in the cosmic background radiation. Circular because it would be the collision of two spheres, and when two spheres overlap, the intersection is a circle. So far, it has not been found, and it's probably not very likely that it would be found, but in principle, it can be found. I think more likely, if we ever do become convinced about the existence of a multiverse, it will probably come out as a consequence of the kind of theoretical arguments that I made here. That is, there are features of our universe that we have trouble understanding, and we also have theories that explain many features of our universe, which also predict that there should be a multiverse. So if those theories are right, you really don't have any choice. Those same theories, unless you find other theories, but the theory of inflation in most of its versions, if those versions are right, really predict that there should be a multiverse. It's not then a choice. You can reject the theory and find something else, but if you're going to accept that theory, it's pretty hard not to also accept all of its consequences, the consequences that you can't observe as well as the ones that you can observe, and that would mean a multiverse.
Wait a second. Listen.
Well, I think that BICEP 2 is really a superb experiment. This is clear. But it has a problem. It operates only in one frequency, at 150 gigahertz. And therefore, foreground emission like dust should change with frequency, but a signal primordial emission should not. Do you think that it should be possible to try to find out in other kind of channels and frequencies with BICEP 3, other kind of signals to be sure that it was really a discovery?
Right. Well, what you're describing is exactly what people are intending to do. BICEP 3 does have more than one frequency, I'm quite sure. And also, the talk about combining the BICEP 2 data with the Planck data is motivated by the same idea. Planck has a number of different frequencies, providing much better discrimination for what's dust and what's primordial. So what you're describing is going to happen. And I think a good feature of all this controversy is that it is almost certainly will be resolved within a year, if not within a month. So I think science is working, and I think we will reach an answer that ultimately everybody will agree on, even though there's been tremendous controversy in the course of getting there.
Here.
Yes.
Alan,
Here.
Alan, here.
A question about the multiverse solution of the cosmological constant problem. So we assume that there will be, in the history of the universe, a couple of phase transitions, say electroweak phase transition, or at least the QCD phase transition. Now, would this solution imply that, for example, there will be a large cosmological constant up until this phase transition will happen, and then the cosmological constant would have been fixed somehow by this 10 to the 500 probability to exactly cancel at the time right after the phase transition? And is this the kind of theory people think about? So there will be a huge cosmological constant all the way up to the QCD phase transition, and isn't that producing too many E-foldings? I mean, does that really work?
Okay. The question is, if we think about the cosmological constant, in the context of a model with many phase transitions, does this anthropic solution imply that the cosmological constant was large in the earlier phases and only became incredibly small in the last phase? And the answer, I think, is just yes. The anthropic argument implies exactly that, because life is only going to form in the last stage, and life is what's crucial to the anthropic argument. So only in universes where, after the last phase transition, the vacuum energy is incredibly small, will you have a long-lived universe that has the possibility of evolving life. That's the way the argument is phrased.
But wouldn't this imply too much inflation because of this large cosmological constant?
Oh, no, the cosmological constant in these other phases would be exactly what we previously think it is, what we currently think it is. Okay, we don't know where exactly this last phase of inflation was, but what we're seeing really is entirely a consequence of the last phase of inflation, wherever it was, and that's the one that has to be long enough to be the 65 E-folds that I mentioned, and whatever happened before that is irrelevant. So the conditions for making inflation work are exactly the same in the context of this anthropic picture of the multiverse as it would be otherwise. It's really not changed.
I just want to make a comment on this discussion. The some quantum gravity of the theory that we have now does explain why the cosmological constant is small, and even gives a calculation that agrees with current observations. So there is a way to explain it using the methods of operator field theory.
I guess what I should have said is that there isn't really a generally accepted way to describe it, and I think that's probably consistent with what you said, right? I think what you're saying is not yet generally accepted. Maybe, but not yet.
Alan, suppose Bicep is not right, because
okay.
Otherwise my question would be nonsense. What do you think about the hypothesis that the Higgs inflation, that Higgs is driving the inflation? The fundamental scalar at 125
right.
is the one that is driving the inflation.
Right. Okay, that's right. One of the features of the Bicep 2 result, if it's true, is that it seems to rule out the possibility that the conventional Higgs particle is itself the inflaton. If Bicep 2 is not correct, that possibility gets revived, and I'm being asked, what do I think about it? The answer, I guess, I'm not sure what to say. I think it's a very interesting idea. It requires a dimensionless coupling constant, Xi, which couples the Higgs field directly to gravity, to have a peculiarly large value like 10,000, I think. So I find that a little bit distasteful, but I think we'll have to wait and see. That is, if that theory is right, we'll be able to get more evidence about it and be able to verify it. Certainly an attractive feature of the idea that the Higgs particle actually is the inflaton is that it means that we'll be able to make a lot of measurements that directly verify the mechanics of inflation, which would certainly be wonderful if true.
Okay. I want to ask your opinion about this entropic solution of the cosmological constant problem. And if we have 10 to the 500 vacua with the correct standard model prediction, for example, from string theory, with only one parameter, cosmological constant variable, then this entropic solution of the cosmological constant is true. But we do not know at the moment any one single prediction from string theory correct MSSM with the Higgs mass, for example, 127. So we must have 10 to the 500 such vacua with only one free parameter. Then this entropic solution of cosmological constant is acceptable. So what is your opinion on this?
Okay. Well, I think the point is that if 10 to the 500 is the right number, and let's pretend it is, and if we have 120 orders of magnitude discrepancy between the allowed range and the probable, the expected range, the Planck scale, that would mean that if things were uniformly or almost uniformly distributed, you would expect that the number of vacua in the allowed range would be 10 to the minus 120 times 10 to the 500, which if you do the arithmetic is 10 to the 380. So that still gives you a lot of chances to get the rest of the parameters of physics right. Now, all of that may not sound terribly convincing, but all we really have to be convinced of here is that it's possible. And then I think we have a possible explanation where possible means the same thing in those two sentences, whatever it was. So to me, it's still a very distinctly possible explanation for why the vacuum energy that we observed might be so small. Okay, I would certainly prefer to have a more dynamical explanation. If somebody can come up with one that's convincing, I'd be very happy. We have a candidate in the side of the room there. And if that happens, great. But I think it really has not happened yet, at least not in a way that has convinced anything like the majority of the particle physics community.
So we have our last question over there.
Excuse me, Alan. I wish to ask you a very simple question I often fail to understand about the prediction of the inflationary model. People often tend to believe that the inflationary model predicts a flat universe. Now, if we look into the Friedman equation, which says that a dot square by a square plus k by a square equal to the right-hand side, if we look into this term of k by a square, now the whole term goes out of the equation because of the exponential expansion of the universe and not because k itself is equal to 0. So k by a squared that goes out of the Friedman equation, you seem to throw out the entire term from the equation by virtue of the exponential expansion, whereas I believe that it doesn't specifically address to the value of k as such, because if it were a closed universe, then k by a squared, the denominator will again come up because a will go down in that case, and then you will again have the resurrection of this term like a phoenix. So I have this impression that inflation as such does not speak anything specifically about the value of k, but it chooses to throw out in a very, wise manner the whole term k by a square out of the Friedman equation, and thereby claiming that you have the flat universe. So could you kindly explain on that?
Okay. I think I understand what you're saying, and if I do understand what you're saying, it's absolutely correct. Inflation does not produce a perfectly flat universe, one that would be described by a Robertson-Walker metric with little k equal to 0. Inflation has no way of making little k equal to 0. But rather what inflation does is it simply stretches the universe fantastically. If the universe started out homogeneous, we could imagine, for example, it's a sphere as a simple model. We could start out with a sphere and stretch it immensely. And when you do that, geometrically, you'd expect that a little piece of the sphere, which is now huge, would look flat, exactly like a piece of the surface of the Earth looks flat, even though we know the Earth is really round. And in terms of the Friedman equations, it would tell us that this curvature term in the Friedman equations has been suppressed beyond belief. So you no longer could see it, and the mass density would be equal to the critical density, and the geometry in a local region would look exactly flat. And that's what inflation predicts. It does not predict that the universe is exactly flat, only that it looks incredibly flat. And that's what we observe. So there's, I think, a superb agreement there between what we observe and what inflation predicts. And I don't think there's any problem associated with the idea that inflation does not make Robertson-Walker little k equal to 0.
Okay, before thanking the speaker again, wait. I would like to thank Professor Alan Gathwood for helping us in this open ceremony. And of course, on behalf of the organizing committee, we wish a rapid recovery to Professor François Langler. Okay, thank you.